Good evening, everybody. So today we are going to see about evaluation of a reaction class using Stoessel's criticality index. So this is a part of safety assessment which need to be performed before taking a specific reaction or a specific process to a manufacturing site. We need to assess the reaction class. Like majority of the times, this is being applicable only for the dosing type of reactions, like where we are going to add a specific reagent into the reaction mass at a controlled temperature. So this is how the index is going to look like. So here totally we'll be having 5 classes, and we are going to classify the reaction using total 4 type of parameters, and the parameters are going to be the operational temperature, MTSR, MTT, and TMR8024. So before going into deep, let's try to understand what are these parameters. So the first one is T process. So this is nothing but the operating temperature. And the next one is the MTT. MTT is nothing but the maximum technical temperature. So this is nothing but the boiling point of a solvent which is available inside the reaction mass. And the next one is the MTSR. So this is maximum temperature to synthesis reaction. And the final one is the TMR AD24. This is nothing but the time to maximum rate. And now let's see from where we are going to get the data. So the first one is the operating temperature. So this you will be getting from the process. And the next one is the maximum technical temperature. So it is nothing but the boiling point of a solvent which is available inside the reaction mass. If there is no solvent, and if you are going to do any neat reactions, in that case you can take the compound with the least boiling point. So this also we can take from the process. And the next one is the MTSR. So it is nothing but the maximum temperatures to synthesis reaction. So this we are going to take from RC1 study. And the final one is the TMR AD 24 hours. So this is nothing but a time to maximum rate, and this we are going to get from a DSC or ERC. And let's see now how to calculate this MTSR from RC1 study. So basically RC1 study is going to be performed for a dosing type of reaction where we are going to identify the heat of reaction. While performing the heat of reaction study using RC1 calorimetry, so we are going to initially take the mass inside the reactor. So it's basically a calorimeter where we are going to perform the reaction steps as per the process, and we are going to circulate a constant temperature utility in the jacket, and depending upon the changes in the utility temperature we are going to identify the heat of reaction, and accordingly we are going to calculate the adiabatic temperature rise. So let's say the total energy that is being evolved from the process is Q, and we are going to calculate the delta T from the formula mCp delta T. So here on this, m is nothing but the quantity of mass which is available in the reactor or the calorimeter, and the Cp is nothing but a specific heat of the reaction mass, and finally dt is going to be calculated. So dt represents the adiabatic temperature change, and we are going to calculate the MTSR using the formula. So MTSR equals to T process plus percentage accumulation, means the amount of energy which is available with the reaction mass even after complete dosing of the reactant, and this percentage accumulation multiplied with the adiabatic temperature rise. So using this formula we are going to calculate the MTSR, and if you are not going to include the percentage accumulation, so you will be getting the MTSR for a worst case scenario. That means this percentage accumulation is going to be 100%. That means the scenario in which you are going to dump the total reactant into the reaction mass at a single instance. It's nothing but a worst case MTSR. So the worst case MTSR equals to T process plus adiabatic temperature rise, nothing but a delta T. So this is MTSR for a worst case scenario. So this is how we are going to calculate the MTSR. And the last one is TMR AD24. So this is nothing but a time to maximum rate. That means let's say from a DSC you got a exotherm, and the exotherm is having some higher enthalpy. That means it's a significant exotherm. And whenever we got some significant exotherm, so we are going to check the onset of decomposition. So let's say the onset of decomposition is approx 220 degrees centigrade, and the enthalpy associated for this decomposition, I mean for this exotherm is, so enthalpy equals to, let's say it's almost 250 joule per gram. As this is going to have an enthalpy of 250 joule per gram, we are going to consider this as a significant exotherm. And the onset of decomposition is observed at 220 degrees centigrade during the DSC testing. And as per a process, we need to maintain for almost 24 hours. And whenever you are going to maintain the reaction mass for 24 hours as per the process, so automatically what will happen is the onset of decomposition shifts towards the left side. That is, it will reduce from 220. So let's say after after maintenance for 8 hours, so the onset is observed at 170 degrees, and after maintenance for 24 hours, so it will be around 130 degrees centigrade. That means whenever you are going to maintain the reaction mass for prolonged hours, so the onset of decomposition is going to be moving towards the left side. That means the onset will reduce. So initially the onset is observed at 220 degrees, and after 8 hours of maintenance the onset is observed at 170 degrees, and after maintaining the same reaction mass for 24 hours, so the onset is being observed at 130 degrees. That means the onset is getting reduced. So similarly, what is the onset or decomposition if you are going to maintain the reaction mass for 24 hours? So that will be represented by this TMR-AD24. So this is like whatever the 8 hours and 24 hours are there, during this scenario if the utility is going to fail, so that's the point. So the condition is going to be where the utility is going to fail. That means the onset of decomposition after 8 hours of maintenance during the case of utility failure. So it is going to be 170, and similarly after 24 hours it is going to be 130 degrees. And it is nothing but the TMR AD 24 hours. And I think till now you have seen about this total 4 parameters and what does this exactly mean. Now let's see about the interpretation of this criticality index. So here in this criticality index which is being shown, there will be total 5 classes, and depending upon these scenarios we are going to classify the reactions. And let's take the first case. So coming to the first case, here if you are able to see, the T process is going to be the lowest value, and it is going to be followed by the MTSR, and it is going to be further followed by this MTT, followed by the TMR-AD24, which means the T process is going to be the lowest end, and then you got a MTSR. So MTSR means it is the maximum temperature up to which the reaction mass will be able to reach. So above this, the reaction mass don't have the potential to reach. I mean, like during any exothermic event, so whatever the energy is being liberated, so that energy will be able to take the reaction mass temperature only to this level of MTSR, and there is no possibility to reach beyond until or unless you are going to give some external supply. Okay, so in this class 1 you don't have, the reaction mass don't have the potential to reach up to this level. And the next one is the MTT. It is nothing but a boiling point. And even though if you are going to give some external energy like the hot water or steam, then what will happen is maybe the reaction mass will gain some potential to move beyond this MTSR, but then also you have the boiling point. That means you will be able to identify the reflex, like whatever the energy that is being supplied, the energy that is being supplied will be used only for the reflex. And once if the total solvent is being evaporated, in such a case there is a possibility that the reaction temperature might reach the decomposition. So this is the decomposition line, and this is a undesired scenario. So we don't want to have decompositions in a reaction. Okay, so coming to class 1, basically your reaction mass don't have the potential to reach up to decomposition. But even though if you are going to provide some external utility, then your reaction mass has the potential, but still there is one more hurdle. It is nothing but a MTT. So MTT means the boiling point of the solvent. So what will happen is, at this particular point, the reaction solvent will try to reflex, and if the total solvent is vaporized, then there is a possibility. So here in this case, there is a 99.99% possibility that there is no chance for the reaction mass to reach up to the decomposition. And coming to class 2, here you got a operating temperature further followed by MTSR. That means your reaction mass have the potential only to reach up to this level. And if you are going to give some external energy, that is the hot water or any kind of steam, then only your reaction mass is going to get into decomposition zone. And here in this case, the maximum technical temperature is beyond the decomposition line. That means once the MTSR is being crossed due to some non-application or some wrong application of a utility, then in such case you can reach this decomposition. So this is also somewhat same scenario compared to 1. And let's come through the criticality class 3. So here in this case, if you are able to see, the least temperature is the operating temperature, and then you got a MTT, nothing but a boiling point. So most of the cases what will happen is, if you are going, like if the reaction is going to be falling into class 3, the maximum temperature that you can operate is going to be the boiling point of a solvent, nothing but a reflux temperature. Why? Because once the total solvent is lost, then only you got a chance to reach up to this MTSR, like the maximum temperature. And then after you got a decomposition. So even in this class 3 also, your reaction solvent is going to keep you in a safe zone. And coming to class 4, here in this case, your reaction mass has the potential to reach into decomposition. But what stops you is the MTT, nothing but a boiling point of your solvent. And once the boiling, due to the total energy that is being evolved, if the total solvent is lost from the condenser, that means in a case where you haven't applied any cooling utility to the condenser and the total solvent is lost, in that case you are in a danger zone. Why? Because the MTSR is beyond the decomposition. That means your reaction mass has the potential to reach up to decomposition, and also if your solvent is lost from the reactor, then you can reach into the decomposition and there can be some serious consequences. And coming to class number 5, so if you are able to see here, so nothing is going to stop you, and also you cannot detect the decomposition. Why? Because your reaction mass is having the potential to reach up to decomposition. The MTSR is beyond the decomposition temperature, and also the reflex, the boiling point of the solvent is above the MTSR. That means nothing can stop you if you are careless. So this is about the classifications, and the final thing is class 1 and 2 is going to be the safest scenarios, and class 3, 4, so this has some concern, but no need to worry if we have some engineering controls in place. And coming to the class 5, so if your reaction is being classified into this 5th zone, so you better get the process into lab and try to re-engineer it. Re-engineer in the sense, so you can make certain changes, or else you can reduce the operating temperature so that it is not going into the decomposition zone. So this is how we are going to classify, or we are going to interpret this Stoessel's criticality index. And now let's try to take a case, and depending upon the case, let's try to interpret, or let's try to classify the reaction. And the case is dosing of a liquid reactant to reaction mass at 120 to 125 degrees centigrade, followed by maintenance for 25 hours at reflux and the solvent is orthoxylene. So this is the case, and for this case we have taken up RC1 study, and from this RC1 study we have identified the MTSR. So this MTSR is approx 135 degrees centigrade, and the TMR AD 24 hours. So let's say this is almost 130 degrees. So this value I have taken from last discussed, so that is nothing but here. And the next one is the MTT, or the boiling point. Here it is nothing but the boiling point of orthoxylene. So let's say it's 144 degrees centigrade, and we got all the values. Now we need to define the class for this, and the first thing is we need to identify the least value. So out of this all, the least value is going to be the operating temperature. So here are this criticality index. So in all the cases the operating temperature is going to be the least value, and then the least value is TMR 80 24 hours. It is nothing but a 130 degrees, and here if you are able to see, in class 5 we found it. I mean, the next least temperature is going to be TMR 80 24 to this T process. So here it is, and the next least is MTSR. So it is 135 degrees centigrade. So this is similar to class 5. Why? Because beyond this TMR 80 24 we found this MTSR, and then we found a MTT, or the boiling point, 144. So the case that we have taken is similar to class 5 here, which indicates this is having high risk, and we shouldn't take this specific process for execution into commercial site. Why? Because there is more chances for a decomposition scenario. So in this case, ideally what we have to do is we have to take the process back. So we have to take the process back into lab, and then we have to re-engineer the process. So re-engineering the process means, so we have to make certain changes so that the risk should reduce from the current scenario. So what I'll do is I'll take the process back into lab, and then I'll try to re-engineer the process by modifying something. Like either I can modify the operating temperatures, or else I can reduce the maintenance time, or else I can change the solvent. So here in this case I found this is a orthoxylene, and I'll try to change this orthoxylene with, or I'll try to replace it with some kind of a solvent like toluene or cyclohexane. So preferably I'll try to modify, or I'll try to replace this orthoxylene with toluene. So in this case what will happen is, after replacing the solvent orthoxylene with toluene, so the boiling point is going to change to 110 degrees centigrade. Now let's try to reclassify the criticality. Now let's see, the least temperature is going to be the boiling point. So here it has reduced. So if you are able to see here, the TMR 80 24 is there. So this is the decomposition line, and previously the maximum technical temperature, nothing but the boiling point, is above the MTSR as well as the onset of decomposition. And now what I have done is I have changed the solvent. So what will happen is the boiling point is going to be reduced from 144 to 110 degrees centigrade. So this MTT will try to get below the onset of decomposition. So now what we can say is, so MTT is below the line of decomposition, followed by the TMR 80 24, followed by the MTSR. Okay, and the main point that we need to find, or we need to identify, is after changing this particular, or after replacing this particular orthoxylene with toluene solvent, so we cannot reach up to this level, like the 120 to 125 degrees centigrade we cannot attain. So we need to reduce the operating temperature also. Reduce in the sense, the maximum temperature that I'll be able to reach is only the boiling point of solvent. So in such a case what will happen is, the operating temperature as well as the MTT is almost going to be same. So in this way you will be able to reduce the risk, and also you can ensure certain controls in the process, so that the process temperature is not going to reach to the onset of decomposition. So here in this case what we have done is we have reduced the criticality from class 5 to class 4. So this is how we need to provide certain mitigation plans whenever there is a high risk due to the available process designs. So thanks for watching the video. If you like our video, please subscribe to our channel, and also please share the videos with your dear ones. If you have any questions or queries with respect to this particular post, so you can write us at pharmacalc823 @gmail.com. So thanks a lot.